Okay, thank you very much. Thank you for your attention. I hope that my presentation will be interesting and useful. Today, I will present my new paper, a new approach to inverse problems for Sturm operators with homogeneous delay, and that paper is published about 7 days ago. So we consider the boundary value problem L0 given by this equation and the boundary value condition with additional condition that potential is zero on this interval where the lambda is spectral parameter. We have here a homogeneous delay and natural number n, and also potential is complex valued. I will back to this slide, but before I want to talk about historical overview. Then I will talk about the motivation and the new approach related to this paper. And also there will be talk about inverse problem and universe stability in the special case. And in the end, we will discuss about open question related to this area. So first, historical overview. One of the central problems in inverse spectral theory is to determine the potential Q of X in the classical Sturm-Liouville operator given by this equation and boundary value condition. A fundamental breakthrough was achieved by Borg in 1946, who proved that the knowledge of two spectra uniquely determines the potential Q of X. This result revealed for the first time that spectral data fully encodes the information about the potential, provided sufficient boundary conditions are taken into account. Later, the theory was extended. Uniqueness theorems were established for wider classes of potential and a more general boundary condition. There are some important books from Freiling Jurko, Levitan, and Marchenko. These developments laid the foundation of the modern theory of inverse spectral theory and motivated further studies, including the case when only a single spectrum is available. Also here I have listed the references I mentioned in the previous slide and this slide. When considering the one spectrum inverse problem, additional information on potential is generally required. In particular, Hörstadt-Lieberman in 1978 and Howell in 1984 proved that a single spectrum suffices to reconstruct the potential provided that it is known on half interval. For example, the spectrum of boundary value problem given with this equation and boundary condition uniquely determines the potential Q of X if the potential is known on this interval. More about the historical review of inverse problem with 1 and 2 spectra can be found in the paper Makarov-Poltoratsky. Okay, next slide. Also, here I have listed some important references I have mentioned on the previous slide. And now I want to talk about the historical overview related to inverse problem for Sturm-Liouville operator with a deviating argument. These are boundary value problems of the form given by this equation, subject to the various boundary value condition. 2 of 3 cases have been studied in detail so far. The first case is when the delta x is equal to x minus a, which is known for the Sturm-Liouville operator with constant delay. The second one when delta x is equal to a, and in this case Sturm-Liouville operators with frozen argument. These 2 cases have been studied in detail so far. And the third case when delta x is alpha x is actually Sturm-Liouville operator with homogeneous delay, and about that operator we will talk in this presentation. But Before that, more historical overview related to um, two spectra inverse problem and Sturm Liouville operator with constant delay. Actually, for a given delay and two spectra of boundary value problem, the goal is to reconstruct uniquely the compressed value potential under a condition that Q of x is equal 0 on this interval. And as I mentioned earlier, these problems are very, very good research so far. There are uniqueness theorem related to the delay. So in the papers Vladičić Pikula, Buterin Jurko, Bondarenko Jurko, and Pikula Vladičić Vojvodić, it was proved that the two spectra are sufficient to reconstruct uniquely the potential Q of x, provided that delay satisfies this condition, and that is the delay is not less than 2 pi over 5. Otherwise, in the case when delay is less than 2 pi over 5, that problem remained open for many years, and series of work Djurić Buterin has shown that two spectra are not sufficient to reconstruct the potential uniquely. Also, we have here important references, and also these three papers related to the small delay. The second case, when actually delta x is equal to a, we have a Sturm-Liouville operator with frozen argument. Also, these operators have been studied very well. The main question is, does the spectrum of boundary value problem uniquely determine its potential? The answer depends on the boundary condition alpha, beta, and the frozen argument a. The author introduced the notation of non-degenerate and degenerate cases, depending on the possibility of unique reconstruction of potential. The classification depends on whether the frozen argument A is rational or irrational with respect to pi. In a non-degenerate case, one spectrum uniquely determines the potential, and otherwise one spectrum is insufficient for uniqueness. Known results in papers Bondarenko, Buterin Vasilyev, also Buterin Vasilyev, Buterin Kuznetsova, and Wang Zheng. These cases were completely analyzed and the precise conditions were obtained, describing when unique recovery of Q of x is possible and when it is not. Also, some of these results are presented on these seminars. Also, there are references that I mentioned on the previous slide. And finally, we can move on the Sturm-Liouville operators with homogeneous delay. They have not been sufficiently investigated. Consider the boundary value problem of this equation and boundary value condition. And for given homogeneous delay and two spectra, the goal is uniquely recover the potential Q of x. The unique recovery of the potential Q of x in these settings remains a serious challenge. Also, this problem was first posed in the two papers, and after more than 10 years, no new results have been published in this area. Unfortunately, in first paper, Pikula Vladičić Marković, serious errors were detected in proof of the uniqueness theorem. And in the second paper, Pikula Vladičić Nedić, the inverse problem was studied under a special additional condition, which later turned out to be equivalent to the case when the potential is identically zero. Since the inverse problem for Sturm-Liouville operator with homogeneous delay highly challenging, a new approach was proposed in the paper that I am presenting now, and after recalling the references, we will continue with the new approach. So here are that paper and also the previous two papers where problem is first posed. Finally, I will talk about motivation and new approach. So, as I mentioned earlier, we consider this boundary value problem, and we have additional condition, which is very important. It is condition 3, and actually that condition is a new approach for solving inverse problem in these kind of operators. Alternatively, we may consider additional boundary value problem L1 defined by equation 1, condition 3, and boundary value condition Dirichlet. Actually, it is the Dirichlet-Neumann boundary condition. So I will speak about motivation with these new settings. Actually, we can try to solve two kind of this problem. One is general problem when for given alpha and n, we try to solve this problem. We try to reconstruct potential from two spectra or from one spectra, depends it is possible or not. But another approach is connection with classical Sturm Liouville operator. Actually, we tried to investigate, is it possible to reconstruct potential where the homogeneous delay alpha is near to 1 and alpha to power n is near to 0. And we use the two spectra. That is one approach. And second approach, when alpha is near to 0 and alpha to power n is near to 1/2, and we try to reconstruct potential from one spectra. So we have clear connection with the classical Sturm Liouville operator. As I mentioned earlier, we have a general problem statement for a given delay and natural number. The first question is investigate whether a single spectrum is sufficient to uniquely reconstruct the potential, and the second question is if the answer to one is negative, investigate whether two spectra are sufficient for unique reconstruction of Q of x. So this is general problem statement, and it is the very rich new theory for solving inverse problems. Also, as I mentioned earlier, we have another approach, and that for given two spectra, it is particularly interesting to analyze uniqueness properties of solution for inverse problem as alpha and alpha to power n approach 1, 0, or alpha and approach 1 and 1/2, and we try to solve one spectrum inverse problem. Okay, we can move on. Next slide. So we in this paper I actually consider the special case, and it is when Q of x is 0 on interval 0 to and alpha pi, and so actually we focused on one spectrum inverse problem and case when n is equal to 1. So we want to see what happened in that case. We consider the following inverse problem given the delay and the spectrum lambda n 0 of boundary value problem L0. Determine the potential Q of x uniquely. Also, the case n greater or equal to 2 is significantly more complicated and requires separate investigation. Of particular interest is to study of the uniqueness behavior of solution inverse problem as this expression approach to 1 and 1/2. So this is the actually first problem to solve these types of problems. Also, as will be demonstrated in the following discussion, inverse problem 1 is overdetermined, and the potential function can be uniquely reconstructed from appropriate subspectrum. So we introduced an alternative formulation of inverse problem. Let nk0 be increasing sequence of natural numbers given delay and subspectrum lambda nk0 of boundary value problem L0 determine the potential function Q of x uniquely. Also, we have here the integral equation 5 that is equivalent to boundary value problem that we actually observed in this presentation. And we can solve this integral equation 5 using condition 4 and obtain this equation, which is very important for characteristic function. So we denote with delta 0 lambda the characteristic function, and that using the previous consideration we get the following result. Actually, this equation is represent the characteristic function. So we are interested in some properties of this function. Actually, we have here some well-known results which are connected to the other non-local operators and related in problems. So the boundary value problem L0 has infinitely many eigenvalues and of the forms. So this is the form of that angle values. And also using Hadamard theorem, we can prove the following lemma, and lemma states that we can recover the characteristic function using the spectral properties, spectral data. Also, we want to solve inverse problem from subspectrum, and we here have some properties of some spectrum. It is also well known from other papers related to inverse problems with other non-local operators. So I will skip this slide. Also, it is continuation of this slide. Okay. Also, we have one important lemma, which is actually first posed in the paper Butanin Yurko, and actually we have some condition when this system Cn is complete in this space, and actually it is equivalent when the system cosine nkx is complete also. Before solving inverse problem, we have to transform characteristic equation, and here we have transformation, and equation 9 can be transformed into the following integral representation. So we have the equation 10, what is the most important equation for our paper. And here the structure function k0 x alpha depends on delay. So we have different structure related to the different delay. Actually, the interval which delay are take values. First, we use important notation that gamma is equal to alpha square minus alpha plus 1. And actually, this is that expression in integral. So the possible cases for function k0 x alpha are described in the following discussion. We have three cases. The first, when alpha is in this interval, we have the simplest structure for this function. The other case, when alpha is from this interval, then function takes this form. It is just a little complicated than previous, and the most complicated case when alpha is in this interval. Also, this structure can announce some problems for solving inverse problem. So the easiest way to solve inverse problem is the first case, and most difficult is actually the third case. Also, we have more notation, and here we have equivalent equation from equation 10. So when we have the spectral data of actually one spectrum, we can recover this function f0. And using that, we will recover function k0x alpha. And actually here we have method for recovering that function. And also this function is very important for reconstruct the potential Q of x. So finally we have the theorem 2. Theorem 2 is the uniqueness theorem for one spectrum inverse problem. Given the delay alpha and the spectrum of boundary value problem uniquely determines the potential Q of x. And for every alpha, we actually from one spectrum can uniquely determine the potential Q of x. So here I want to just mention that I also investigated the Dirac operator, the homogeneous delay, and we can not achieve this result. And I think that it is first result related to operators with delay when we consider the Sturm Liouville operator and the Dirac operator, and we don't have same result related to the delay. So I think that it is important result related to non-local operators and inverse problems also. Okay. I will skip the proof actually of this theorem, but using the spectral data, we can construct that function, and from function k0, the potential Q of x can uniquely be recovered. As I mentioned earlier, in this case, reconstruction is not difficult, while for the case when alpha is less this value, the situation is much more challenging. Also, more details you can be found in this paper. Okay, and now we will talk about reconstruction from subspectrum. So here we have important theorem and that actually states that potential can uniquely determinate by subspectrum of the functional system if the functional system is complete in this space. So actually that is important condition. Also here we cannot prove otherwise, and because this function k of 0 x alpha has the special structure, so it is impossible to prove other side of this theorem. But this is also enough for this result. Also, I have here the proof of that theorem, but the methods are also similar to the other Sturm Liouville operators with delay. And the main point is to reconstruct the function k0, which is possible in this case. And when we construct this function, then using the proof of theorem 2, we can reconstruct the potential of Q of x. So that's the main idea. Also, I want to say some words about the uniform stability. So in this paper also I consider the uniform stability of the inverse problem, and the uniform stability of non-local operators was first investigated in the papers by Buterin. Later this approach was applied to other non-local operators in papers Djurić, Buterin and Wang Yang. A key component of this method is to demonstrate the uniform stability in recovering the characteristic function of operator under consideration from its zeros. Also, this result was extended to arbitrary sign type function with asymptotically separated zeros, and it was published in this paper. Okay. These are the references I just referred to, very important references related to uniform stability of non-local operators. And here actually we have the lemma of uniform stability. It is actually statement of theorem 1 in this paper. And so it is very important lemma for the proof the uniform stability of inverse problem for Sturm-Liouville operator with homogeneous delay in these settings. And this theorem for this is formulation of theorem 4 related to uniform stability. Also, here we obtain a result similar to the uniform stability for Sturm-Liouville operator with constant delay and others non-local operator, and we employ analogous methods with improved technique. So I will skip the proof of this theorem. Maybe much more interesting for this presentation are open question related to this area. And so in this presentation, we have studied the inverse problem associated with the boundary value problem L0 for the case where n is equal to 1. And in this setting, the characteristic function depends linearly on potential q of x. Moreover, we have shown that single spectrum or subspectrum is sufficient to recover the potential for any delay. However, for case when n is greater or equal to 2, the characteristic function exhibit of nonlinear dependence of q of x, and the case n equal 2 is already challenging, and each other step increases in complexity. Even in the case n equal to, it is interesting to investigate for which value of delay alpha the two spectra do not contain equivalent information. However, as I mentioned earlier, we can consider the general problem statement, and we obtain a very broad and rich class of inverse spectral problems to investigate. And also, I would like to encourage younger researchers to explore this area. And a particularly interesting case to study in the inverse problem when the homogeneous delay is close to 1. Most precisely, we formulate a special class of inverse problems for Liouville operator with homogeneous delay, and here we have two formulation. So for fix n, determinate the value alpha n such that for every alpha in this interval, one spectrum uniquely determines the potential of boundary value problem L0, where alpha n to power n is near to 1/2. And another formulation of two spectra inverse problem for fixed n determinate alpha n such that for every alpha on this interval, two spectra uniquely determines the potential of the boundary value problem L0, where the alpha n to power n is near to 0. So I'm not formulate this precise because I use the word near, but I think that the point is clear about this. And also this formulation is actually related to the graphic in the previous slide. I will back to that slide. So I'm back now. Okay. Actually, it is connection with the classical Sturm-Liouville operator. And so if we can construct the sequence of alpha to power n such that for every n, this sequence tends to the 0, and we can recover this operator from two spectra, it would be the great result. And also the case when we can construct the sequence of alpha to power n, when alpha to power n actually tends to 1/2, and we can recover the Sturm-Liouville operator with homogeneous delay from one spectrum, that is also the great result. And I think that I'm very close to solve this second problem, this problem from spectrum. And I hope that also I will publish that paper soon. But for now, it's only my opinion, and we will see soon is it actually possible to reconstruct. So we have a lot of new problems. We have general problem statement here, and also we have special cases that have a clear connection with classical Sturm-Liouville operator. And so I hope that we have new classes of problem that will be interesting for solving for other researcher. Okay, thank you. Any question, comments are welcome.